So I will talk today about teaching logic programming in the era of generative AI. I'm Paul Tarao, and this is for the PEG 2024 workshop. Let me start with the generative AI disruption of education that we are facing it at multiple levels. Partly comes from our current educational technologies and not being ready for the sudden problem-solving capabilities that AI can bring. And of course, the evaluation mechanisms then will be very easily cheated via the presence of strong AI, especially for essay writing or for any kind of canned content, multiple choice questions. Also because of the tradition that's pretty long time ago about sometimes replicating memorized content and lack of emphasis on what I call actionable generalization. Generalization that's coming not just from the patterns that much, but a generalization that comes from some deeper intuition and connections. An interesting thing here related to the disruption is that some of the things that are actually disrupted deserve to be disrupted because they are not the best of the educational process in a way. An example that comes to my mind here is about thinking fast and thinking slowly. Well, quantity encourages thinking fast, watching patterns, reacting, but then deeper understanding of the content means thinking slowly, and that's very true, especially in logic and even more in mathematics. So to advance on the let's see what's happening here. The specifics of the AI disruption on the student testing. Of course, traditional plagiarism detection methods become ineffective. Homework practices get very easily disrupted. There is an example in the paper about, well, the cheater's paradox, in which even if there is a degradation of the exam results, homework-based grading can make the cheater end up with a higher grade than an honest learner. Let's look now at the domain-specific disruption, which is our interest here, Prolog. Well, LLMs write nice Prolog code when prompted in plain natural language. And this is also based on the background knowledge that's encapsulated in the LLM's knowledge base, live memory. So here I'm asking kind of a medium level Prolog program that finds the first pairs of twin primes and show the result it returns. So the background that's important here is that it knows about primes, which let's say it's no big deal, but then twin primes, all you have to say is twin primes, and it knows that there are primes that there is a difference of 2 between them. So the program is split nicely into a first part here that's basically a definition of primes, followed by a specific um, definition of twin primes, and then all organized nicely and a very readable code overall. And that's just a random example. So the disruption is there, and here are some thoughts on the logic of joining it rather than, let's say, resisting it. Well, generative AI denial is a natural, partly rational, partly emotion-driven reaction of people working in symbolic AI, natural language processing, and even classic machine learning, because they are prime disruption targets of it. It suddenly deprecates years of hard work on significant academic and industrial achievements, natural language processing, and other examples are clearly victimized by the superior quality of the AI-induced equivalents. Now, on the positive side, and I would try to emphasize that, especially related to the Prolog and logic programming, the teaching process, is that there are natural synergies between logic programming and generative AI. And if we look at this aspect of teaching Prolog and related languages, we can see a few pragmatic steps for joining the disruption rather than denying or fighting it. Let's look at engagement strategies for AI assistants. They can be used as evaluators, on-the-spot helpers, tutors, more elaborate learning process. This is involving tutoring, code readers, and we have seen them as code writers, but they are very good code readers as well. And then playmates in a gamified learning board, for instance. We'll elaborate more on gamification a bit later. So let's look first at basic AI engagement strategy. So we have the generative AI agent with us, and we want to use it, but sparingly. So the basic engagement would be that we learn the underlying concepts first, try to solve the problem. If stuck, we iterate a few times. Still stuck, we call the AI assistant. After reading the solution, answer a set of multiple choice questions about the AI's code. So there is still some involvement there that's possibly gradable. In the case of Prolog, this AI-assisted coding pipeline can be refined by requiring the students to run the AI's code and, let's say, explain the results of a few spy points by tracing the execution in some critical parts of the AI-generated code. Of course, more interactive online engagement platforms like Canvas, for instance, could bring discussion groups where the AI-generated code is discussed between students, some kind of forum, and then this interaction between students is also gradable by either the instruction or even by an automated AI assistant. Gamification now. Well, relies on borrowing elements from the gaming world students are naturally exposed to. An assignment would request a small group of students to compare a Prolog program given by each to a different AI of their choice. The students will be timed on testing and possibly debugging the AI provides solutions, and then gain points and banners and, well, like in video games. The students discuss the merits and demerits of each in a forum, also with a partial grade originating from their participation in the forum. Possible refinement of the grading is to allow AI assistance, and that's kind of like using magic spells in a game. You can do it, but there is a point cost. And one of the way to rebuild your strength level would be by doing some extra work, which obviously brings, in this gamified world, clear learning benefits. Well, we know that logic and natural language are very closely related, partly because, historically at least, logic notation originates in natural language. We have those natural mappings between verbs and their, well, predicates and predicate arguments and nominal groups. This is especially relevant when we are solving knowledge representation problems. So that hints towards learning methods and language constructs that could be mapped easily, either syntactically or semantically or both, to natural language equivalents. So my experiment along those lines is NatLog. That's a lightweight natural language inspired Prolog dialect. Here's an example of code, very flat liberal syntax. This can be seen as a predicate, but it's basically words, and there is, in fact, the equivalent of higher order programming. Anything in any position can be a variable, so we do not have the constraint that predicates need to be necessarily predicates by things that are in the first position to be necessarily constants. And then we don't need to hyphen names together. They just need to be the same text for it to be recognized as a component of a statement. And that's the definition here. And then here is the usual decomposition: grandparents of XGP, parent of XP, parent of PGP. The definition of ancestors, also carefully recursing without too much repeats, very readable, a bit more readable without the parenthesis overload that Prolog, conventional Prolog syntax provides. So NatLog also opens access to Python's rich finite set and corroutening primitives, so it's not a toy language. Example of NatLog code defining a source level find all three. You make a stack by just calling the list operation in Python. That's how you call a function that returns something. That's a method call that appends something to a list. That's the push operation. It would not return a result. It just does it. So it's a procedure. Pop is the same thing here, but it returns something. And then find all would be just the list of XGS. So those are the patterns that you want to implement, and then a collection to a stack that is then returned. There is, of course, copy term and everything going under the hood, but all those happen easily in Python with very complex calls. So that tells you that it's a relatively expressive language with minimal annotation to connect to Python. If you put two quotes, back quotes here, then you can call generators, and then they will backtrack over multiple answers. So there's a natural mapping between things like generators in Python and Prolog backtracking mechanism. Another system that relies also to this connection to natural language is deep LLM. Deep LLM automates step-by-step reasoning in an LLM dialogue thread by recursively exploring alternatives, these are OR nodes, and expanding details and nodes up to a given depth. And we recognize here the very basic horn-clause logic. There are use cases ranging from consequence predictions, causal explanations, and particularly interesting is topic-focused exploration of scientific literature and causal explanations also. Let me show you a very simple example of exploring a topic with deep LLM. Again, we want to know about, let's say, inductive definitions, now that they are also used in the semantics of Prolog, and it might be taught in a Prolog course about, semantic of Prolog based on inductive definition. We have a horn-clause form here that tells that an inductive definition is either something like this or something like that or something like that. You see the OR notation here. Or in the case of further exploring an AND node, base case specification involves recursive structures initialization, minimal instance configuration, and so on. And all this comes from the deeply recursive exploration of the knowledge base that exists in any reasonable LLM at this time, including some small LLMs, not very small, like let's say Mistral or Llama 3, any of the major LLMs perform really well on this. So what we get basically is a propositional horn-clause program that's usable on its own. And we get also an associated relation graph where we have things that come directly from the horn-clause structure, the definitional part here. But the LLM is also asked to make connections a little bit out of the box, mathematical inductions, induction principles, is logic, or they are like hypernym, like generalization, or inductive assertion method is a formal verification method. So those would be connections that try to put things in a context. Well, teaching with multi-agent AI systems, a trend in today's large-scale industrial strength API is to bring in the generative AI to write custom code, vector store and database calls, LLM API calls. The combination of all these brings us to a society of specialized AI agents. For instance, in the case of Prolog, we have a code generator assistant, a code critique, and bug finder, natural language from executable Prolog translation, conversation animator, an AI bot as part of team projects or forums, instructor representative as a performance evaluator. So this is a sketch of, there's more in the paper, about bringing in multi-agent systems. Of course, very important is to have the human in the loop. That could be, in this case, depending on the scale, instant connection to the instructor, or less direct asynchronous, let's say, event queue or Blackboard-based mechanism that brings instructor intervention, but the AI would provide an executive summary of what went wrong with the student that got blocked on a given problem. Well, some out-of-the-box things finally. Transitions from penalty-based to reward-based teaching. In the training loops of today's user-facing LLM, reward-based engagement has plenty of room. Encourage emergence of spontaneous social network study groups exposed to diversity of teaching systems. Facilitate curiosity-driven AI-assisted self-study. There are systems like character AI agents where the individual's curiosity on a school topic can be explored directly and turned into a learning process while interacting with the customized agent aware of past interactions with its owner. Industry-inspired project-driven learning using GitHub pilots when the deliverables in a graduate course, for instance, are artifacts. It's perfectly fine to bring in the AI as a power enhancer for coders. And of course, moving from canned routines and memorized factoids to actionable knowledge outcomes that I mentioned before. So here's our conclusion. Well, generative AI is a major disruptor, not just of industrial fields and research fields, including symbolic AI as we know it. We have a twofold impact on teaching Prolog. Impact on the teaching itself, and of course, impact on the domain. And they can be brought together, and their synergies can be exploited. In particular, with LLMs being able to write clear and well-explained Prolog code, it makes sense to join the disruption and invoke them as helpers at various stages of the instructional process. Some of our suggested teaching techniques and also some of our out-of-the-box ideas will take some time to migrate from the realm of the possible to the realm of the real, but the road to get there is wide open. Thank you very much.